Okay, let's get started. So today we're going to go through some of the common mistakes in class test 1. Okay, so even if you didn't make these mistakes, please just make notes. Okay, so I did see quite a few students making these mistakes, so we don't want these made next time. Okay, then after that we'll go through some more antiderivatives work from the tutorial. Okay, remember that the tutorial is compulsory and you will need to hand in your work to the tutors at the end of the session. Okay, so for question 1, most of the students answered this alright, okay, so that's fine, but there were a few mistakes. So for questions 1 and 2, students are still leaving the answer in terms of the trig function. Okay, please don't do that. We want the answer in terms of x. So for example, with just number 1 here, if we have y prime is equal to 2x over sec squared y, many students were leaving it at this point. This is only half the answer, okay? You're halfway there. You need to write it in terms of x. So this bottom part, you would write in terms of x, and you would get 2x over 1 plus x to the 4. Okay, so the full solution is available online, but just to say that a lot of students didn't finish the question. Okay, same thing for number 2. Again, students didn't finish the question. For number 3, I saw a lot of students were getting confused with using the product rule and the chain rule. Okay, like I said when we were doing this implicit differentiation, don't do too much on one line. So if you have to use the product rule and then the chain rule, or you have to use the chain rule then the product rule, do it over separate lines. You don't have to do everything on 3 lines. Okay, so let's just do for the left-hand side of that problem. We had d by dx of xy tan x plus y. So we see we have a product of 3 functions. So the x, that's the one, y, that's another, tan, that's the third one. But inside tan, we've got more stuff going on. So apart from using the product rule, we also need to use the chain rule for tan. A lot of students were trying to do everything at once, and then they left things out. So let's start by using the product rule, and then leave the chain rule bit for another line, so we don't mix things up. So differentiating the x, we get a 1, and then everything else stays the same. Okay, we leave it 1 by 1. Okay. Plus, and then we have the x, we leave that alone, we differentiate the y. So it will be x, sorry? It's? Oh, yes, sorry. Yeah. Let's get rid of that. Cool, just see me afterwards, I can give you some points for that. Okay, so that's the y. Plus x, and then we do the y prime, tan x plus y. So then we differentiate the second one, and then now we differentiate the third one. So xy is the same, and then it's going to be d by dx tan x plus y. So I'm not going to evaluate that, I'm just going to leave it as the derivative, because I know that I'm going to have to use the chain rule. Okay, so here we did the product rule on this line. On the next line, we can then do the chain rule for that last term. But the nice thing is, all those other terms stay exactly the same. We don't have to worry about them. So we have y, tan x plus y, plus x y prime, tan x plus y, plus xy, and now we can do the chain rule part. Everything else stays the same. That's already done. So the derivative of tan, that's going to be sec squared. And then we need to use the chain rule. We differentiate the inside. The derivative of x, that's going to be 1. The derivative of y, that's going to be y prime. Okay. So now we haven't made any mistakes. We've done the product rule on the one line. We've done the chain rule on the other line. Okay, if you are comfortable with doing everything on one line, please do so. I'm not going to stop you. But if you are struggling with knowing when to use the product rule, when to use the chain rule, please separate it out as much as possible. Okay. Okay, so that was quite common. For question 2 on the limits, I see a lot of students are not checking if you can use L'Hopital's rule or not. So for this first one, so this is for question 2. So for the first one, we have the limits as x goes to infinity, x sine 1 over x. Now the first thing we should do is check if we can use L'Hopital's rule. You don't just apply L'Hopital's rule because it's a limit. Remember, there's quite a few techniques when finding a limit. There's that direct substitution. If it's continuous, you can use the squeeze theorem, you can use L'Hopital's rule, there might be more. So don't always just go straight for L'Hopital's rule because you see a limit. You need to check first. So here, if x goes to infinity, this first term, this goes to infinity. What about the second one? The sine function is continuous, so we can look inside. 1 over infinity, that's going to go to 0. The sine of 0 is 0, so that means this goes to 0. So we have infinity times 0. That's an indeterminate form. We can use L'Hopital's rule. If this was something else, like 0 times 0, that's not an indeterminate form. You don't need to use L'Hopital's rule. So please check for L'Hopital's rule before proceeding. So look, you don't need to write it out, but just look. So x, that goes to infinity. The sine, that goes to 0. I have an indeterminate form. I can use L'Hopital's rule. Okay. If it's something else, like sine x over x, where x goes to 0, we did this before. You can't use L'Hopital's rule because you end up going in those circles. So here we use the squeeze theorem. Okay. So you need to be able to identify what technique to use for what limit. Okay, so that was number 1. Quite a few students got that, which was good to see. Number 2, we have here L is equal to the limit as x goes to infinity, 1 plus 1 over x squared to the x. Okay, so this is also an indeterminate form. Okay, 1 to the infinity. And that was on that table that we had. So here we can use L'Hopital's rule, but it's not in the correct form. This is in the form 1 to the infinity. We need it in the form 0 over 0 or infinity over infinity. Now, like I said here before, when you have your f of x to the power g of x, what we want to do is get that g down to the bottom. So how do we get exponents down? That's a log law. If we take the natural log of this, we're going to get g of x, that comes out of the log, and then we have the natural log of f of x. And then with a bit of more manipulation, you can get this into the right form. A lot of students were just differentiating this as is. Okay, you can't do that. For one, this is not a number, so you can't use like the exponent, so it's not 2 to the x to differentiate, and it's not something like x squared. So you can't use your exponential rules, you can't use your power rules, you can't differentiate this easily. Okay, so please don't directly differentiate this. Okay, that's not anything that we've learned before. Okay, other questions, number 3, that was answered quite well, except when we have something like this, x goes to infinity, e to the x minus 1 over x squared plus x. Okay, first thing we do, x goes to 0. First thing we do is we check if we can use L'Hopital's rule. What happens in the top? We get 1 minus 1, which is 0. In the bottom, we get 0 plus 0, which is 0. It's an indeterminate form. We can use L'Hopital's rule. So this becomes e to the x over 2x plus 1. Now, if we substitute 0, we get 1 over 1. That's not an indeterminate form. So we don't use L'Hopital's rule again. We have our answer. This is fine. There's no problem. A lot of students were doing L'Hopital's rule again, and we're getting e to the x over 2. That's wrong. Going from here to here, there's no reason to use L'Hopital's rule. There's no indeterminate form. There's no problem with the limit. That shouldn't be done. Okay, so I gave those students a mark for the first step, but then the second step is wrong, so you didn't get the full marks for that. Okay, please don't do that. Question 3, that was right, except when taking the derivative, we had f of x was e to the x tan x. Okay, a lot of students were writing this derivative as e to the x sec squared x. Okay, that's not the product rule. If you have a product of two functions and your result is a product of two functions, you've done something wrong. If you have the product rule, you should have f prime g plus g prime f. We're missing something here. We only have one term. There's something wrong. So here, when we take the derivative, we need to take the derivative of the first term, leave the second term alone, plus we leave the first term alone, and we take the derivative of the second. Okay, a lot of students did do this, okay, so that's correct, but there were, I think, around 5 or so that were leaving it as e to the x sec squared x. The problem with that is everything afterwards is wrong, because if you get the derivative wrong, then your tangent line is wrong. If your tangent line is wrong, your error is wrong. Everything after that's wrong. Okay, so you can get 1 mark for knowing the method, but all your calculation is wrong after that point. Okay, so please double check your derivatives there. Okay, with question 4, that was done all right. Question 5, most students got that, except some students were confusing the related rates with error approximation. If you have some function v of r, and you want to approximate the error, we use differentials. So it's going to be dv is equal to dv by dr. That's an r. And then we approximate this by our delta v. So from an infinitesimal dv to some finite delta v, dv by dr delta r. Okay, many students did get that. A lot of students were confusing this with rates of change. So they were writing dv by dt is dv by dr by dt. There's no time. The question had a cylinder, you were measuring the radius and there was some error. Or you're measuring the height and there's some error. There's no time involved whatsoever. You should not be doing any time derivatives or any other derivatives. Okay, this is wrong. There's no time involved in these approximation questions. The only time you have to find dv by dt if it's a rate of change. And the question will say the rate of change of the radius or the rate of change of the volume. Then you know it has something to do with time. If it's approximation or error approximation or relative error or something like that, then it's differentials. Okay, so they might be similar, but please do not mix them up. Okay. And then I think that was it. So that was the major mistakes for the class test. Okay, again, even if you didn't make these mistakes, please just make notes of them so you don't accidentally make them next time. Okay, so this is where most of the marks were lost in the test. If you are confused with any of this, or you've looked at the memo and you're still confused, please just email me or see me in my office. I'll be happy to go through it with you. Okay, even if you have to redo the whole test in my office just to make sure you know it, that's fine as well, right? So if you want to book a whole hour-long session to go through the work, I'm fine with that, right? I'm here all day. Please make use of that time. Okay, so in the last lecture, I went through some of the students that got the higher end marks, so 70s and 80s. If those students would like to say something about what they did, or if you've got any advice for the other students, please just put your hand up. So maybe you know some websites that you use that's helpful, anything like that. If you would like to share that, please let me know. Okay, so there were students with 75, students with 85. If you would like to help the class with your secret knowledge, please. Okay, you're going to keep your secrets. Okay, no problem. Let's go on to today's work on antiderivatives. Okay, so quick recap on what an antiderivative is. It is the reverse process of taking a derivative. So if we have some function f of x, we can take the derivative and we get f prime of x. Okay, so going in this direction, it's going to be the derivative as we know it. Going in the other direction, we call that the antiderivative. Maybe a better name would be the reverse derivative, but we call it the antiderivative. Okay, so going in the reverse direction, we have our little f, and if we want to find the antiderivative going in the other direction, we typically call it capital F of x. Okay, there is another notation for this, but we're only going to cover that later on when we do integrals. So for antiderivatives, the notation is capital F. If you have a little g as your function, then the antiderivative will be capital G. If you've got a little h, then it's capital H. Okay, so that's the notation that we use. Okay, and there were some rules that we found with taking the antiderivative just by reversing that process. So when we took the derivative of x to the n, so here, derivative, on the other side, antiderivative. Okay, so x to the n, if we take the derivative, it will be n x to the n minus 1. Okay, we know how that works. For the antiderivative, if we have x to the n, that becomes x to the n plus 1 over n plus 1. Okay, so it's the reverse process. Instead of subtracting 1 from the exponent, we add 1. Instead of multiplying by that exponent, we then divide. Okay, it's just the reverse. Okay, the derivative of sine x, that was cos x, and the derivative of cos x, that's going to be minus sine x. Okay, we know that, we've done that many times before. Now, when doing the antiderivative, we want to go backwards. So if we have cos x, the antiderivative, we just look backwards along the arrow, we get sine. So cos x goes to sine x, and sine x goes to minus cos x because we've got this minus sign here. Okay, if we multiply both sides by the negative, we see that going in the opposite direction gives us minus cos x. Okay, please do not mix them up. Okay, if you do have a question and you mix this up like at the top, your mix-up is going to make everything else wrong going down. So please do not make that mistake. Okay, then with antiderivatives, we had those other trig functions. Please go through that yourself. We had other ones as well. We had 1 over x. This was our special case. So it's not one of those x to the n type situations, because here we would have x to the minus 1. If we added 1 to the exponent, it would be x to the 0. Then we would be dividing by 0, and that's just a big problem. But we found another way of evaluating this using those inverse functions. Remember, the derivative of the natural log was 1 over x. So the antiderivative of 1 over x is the natural log. It goes back and forth. So this goes to the natural log of x. Okay. Please make sure you include these absolute values here. So the antiderivative of 1 over x is the natural log absolute value of x. Okay, so for now I'm just going to leave it like that. When we do integration later on, I will explain where that comes from. But for now, you can just remember it as a rule. Okay, and then this was the reverse here. If we have the natural log of x and we take the derivative, we get 1 over x. Okay, so that was the main functions that we see. And then we extended this a bit. So if we have e to the kx for some constant k, we know that when taking the derivative, it will be k e to the kx. So the reverse process would be not multiplying, but dividing. So e to the kx, that will become 1 over k e to the kx. Okay, and a similar thing happens with the trig functions. So if we have cos 2x and we want to find the antiderivative, that will be 1/2 sine 2x. If you take the derivative, you multiply. If you take the antiderivative, you divide. Okay, so we can write that down here. If you have sine kx, that becomes k cos kx. We've always multiplied that because of the chain rule. And if we have cos kx, that would be minus k sine kx. Okay, and then for the antiderivative, you divide instead of multiply. So here, sine kx, that's going to become minus 1 over k cos kx, and then cos kx, that becomes 1 over k sine kx. Okay. So we have the usual behavior like with that e to the kx part. Right, any questions on this so far? Okay, so if you ever get stuck, just think about this table bit on the left-hand side there with the derivative. If you know the derivative going one way, you already know the antiderivative going the other way. For example, like we said last time with tan and sec squared. The derivative of tan is sec squared. The antiderivative of sec squared must then be tan. So even if I don't write it down, you still know the answer because you know what the derivatives are. Okay, and the same thing happens with sec tan. I think that's in your tutorial. Okay, please look at that. Okay, let's have a look at a few of the problems in the tutorial. So I won't go through some of those easier problems, like with the polynomials, but there are a few that are a bit tricky. Okay, so the first one is if we have f of x is equal to x times 12x plus 8. Okay, so this isn't in standard polynomial form. Since it's not in standard polynomial form, we can't do that power rule on each term because we've got a product of terms. Okay, now next year we'll learn how to do this in general when we have a product of two functions. But for now, there's always some trick that you can use. In this case, if you got a product like this, just multiply it out. Okay, and then you have a polynomial in standard form. So here we have 12x squared plus 8x. Now we can look at it term by term and find the antiderivative. So even though this first part looked a bit difficult, if you just multiply it out, you get something that's easy enough to do. So in this case, it will be f of x capital, right, for our notation that we're using, is going to be 4x cubed plus 4x squared plus c. Please do not forget the plus c. Okay, you have to put that because, like I said last time, there's not a unique antiderivative. It's a family of antiderivatives. One for each value of c that you can put in. Okay, please put that in. Okay, similar to this, another problem from the tutorial. We have x minus 5 squared. Okay, again, later on we're going to learn how to do this in general, but for now, since we've got this inside function and outside function, it's a bit confusing, just multiply it out. Once it's in standard form, you can then carry on as usual. So this will be x squared minus 10x plus 25. Now it's in standard form, you look at it term by term, and you can get your answer. So capital F, that's now going to be 1/3 x cubed minus 5x squared plus 25x, and again, don't forget your plus c. Okay. Okay, so again, you just go through it term by term, and you do your power rule. So you add 1 to the exponent, divide. Okay, if minus 10x, you add 1 to the exponent and divide. For 25, there's no exponent, but we know from last time that it should be 25x, because if we take the derivative of 25x, we get back to 25. So we know that's right. Okay, now you can leave your answer like this. That's where all the marking will stop. But for your tests and assessments and so on, please make sure that you check your answer. Do not leave it like this. Take the derivative and check that it matches with what you started with. Okay. Okay, so you won't lose any marks for not checking, but if you do check, you can clearly see if it's right or not, and then you guaranteed those marks. Okay, plus if you do get things wrong, at least I can give you some part marks for checking. Right, if you get the derivatives correct, I can give you something for that at least. Okay, another one, let's see here. Okay, so we have f of x is equal to 3 root x minus 2 cube root x. Okay, something like this. Now, again, you might think we can't use the power rule, right? There's no powers to speak of here. But the root of x is the same as x to the half. Now, we can use the power rule. The cube root of x is x to the 1/3. Again, now we can use the power rule. So let's rewrite this as 3x to the half minus 2x to the 1/3. Now we can use the power rule with that. Okay, so capital F, it's going to be 3 times, okay, we have a half, we're going to add 1. A quick way of adding 1 is to think of the 1 as 2 over 2. So it's going to be 3 over 2. We need to divide by 3 over 2, so that's the same thing as multiplying by 2 over 3. Okay, just do that in your head a number of times, and it will become automatic eventually. And then it will be x to the 3 over 2. Minus 2 times x to the 1 over 3. We're going to add 1. Think of that as adding 3 over 3. So we get 4 over 3. Divide by 4 over 3. That's the same thing as multiplying by 3 over 4. X to the 4 over 3. Okay. If you finish all of the tutorial questions, I promise you this will become automatic, right? Adding 1 to the exponents and dividing, you'll go through it very quickly. Okay, the first few times it's a bit difficult knowing what to do, but it does become quite easy afterwards. Okay, you can leave your answer like this, or you may want to simplify if you have to do further work. But this is fine as is, but again, if there's follow-up questions, you might want to simplify. So here we can write this as the 3 and the 3, they cancel, so we have 2, x to the 3 over 2, the 2 and the 4, so we get 3 over 2, x to the 4 over 3 plus c. Again, it's not compulsory to simplify, but if there's follow-up questions, maybe it would be easier to do that. Okay, another one, f of t, that's going to be 3 cos t minus 4 sin t. Okay, so here's where issues start coming up, when we've got things like minus sine, because we know there's that sine issue. When you're taking the derivative of sine, you end up with cosine. When you take the derivative of cosine, you end up with minus sine. It's the opposite for antiderivatives. So here, if we ignore the minus, okay, so just ignore that part, we have 4 sin t. The antiderivative will be minus cos, but we already have a minus, so it will be minus minus. Okay, so please, if you've got a minus in front of your trig function, think about how many minuses you actually have. So here, your antiderivative will be 3 sin t minus, and then we have another minus. Okay, so if you find that tricky, put both minuses and then have the other one in brackets, and then on the next line simplify. But don't try to do it so quickly that you end up writing minus cos t and then everything's wrong. Okay, so this is minus 4 cos t plus c. Okay, now there's less chance for mistake. Now the minus and the minus, now it makes a plus like we said. So this will be f of t is 3 sin t, minus and the minus, that makes a plus, 4 cos t plus c. Okay. Okay, so sometimes it is helpful to do things over multiple lines. In this case, it's this minus sign in front here. Also, if you have the minus sign in front of the cos, don't confuse that with derivatives, right? So the derivative of cos, that's minus sine. The antiderivative of cos is just sine, not minus sine. So if there's a minus in front here, it stays, because there's no two minuses. Here we've got two minuses, and then it becomes a plus. Okay, so please, if you do need to do it over multiple lines, put the brackets here, and then you can see. Okay, one more. So we have f of x is equal to 1 plus 2 sine x plus 3 over root x. Okay, the first two, not so bad. Just remember with the sign, is there a minus, is there not a minus? Don't mix that up. Here, the 3 over root x. The root x we can write as x to the half. But since it's in the denominator, we can take it to the numerator, but then we get that minus for the exponent. So we can write this as 1 plus 2 sine x plus 3 x to the minus 1/2. Okay, just because you see a root x doesn't mean it's automatically a power 1/2. If it's in the denominator, the power is minus 1/2. Okay, so please don't mix that up. So now we can find the antiderivative. So that will be x. Good, someone said that there. Next one, anyone want to say that? Minus 2 cos, good. And then here, since the exponent is minus 1/2, we're going to add 1. Think of the 1 as 2 over 2. So it's going to be, the new power will be 1/2. We're dividing by 1/2. That's the same thing as timesing by 2. So the 3 will become a 6 because we're timesing by 2. And that's x to the 1/2 plus c. Now, if you want to rewrite that as root x, that's fine. If you want to leave it as x to the half, that's fine as well, right? That's just up to you. Okay, personally, I leave my answers as x to the power something. So in the tutorial solutions and the test memo and so on, I'm going to leave it like that. Okay, but if you want to rewrite it as root x or cube root x, that's fine as well. Okay, yes?
So when do you know to use that method to enter that into the natural log?
So the natural log, if we go back here, that was the special case. It is only for this. Okay, so 1 over x, that is the only time that you use the natural log. Anything else, fractional exponents, negative exponents, positive exponents, we use this first one. Okay, so the only time we don't use that first one is when that n is -1, then we have 1 over x, and then we use this, the natural log. Okay, so big star over here, this is our special case to the power rule. Okay, yeah, good question. I do see that quite a lot. Students try use the first rule, even though it's x to the -1. Okay, please don't do that. Okay, and again, always put your plus c. Okay, any other questions? Okay, so everyone's okay with antiderivatives. Okay, if you have an issue with antiderivatives, please speak up before we go on to the next chapter. Okay, because we won't be going back to this. Okay, so we're going to start the new work.